computer. Thank you for that. Who was that?
That was Jace.
Hi, Jace. Thank you for reminding me. Okay, so the motivation behind the relative true error was that classic example where if you had if you did a measurement of something that supposedly should be 100 feet and you committed an error of 1 foot, and then you measured a table that's 10 feet and you committed a 1 foot error or in the measurement of that table, then both errors have the same value. They're both 1 foot, right? But which one is more grave? It's the error on the table with the table. Why? Because 1 foot out of 10 feet is significant. It's 10%. It's 10% of the 10 feet is a significantly bigger error than 1 foot versus 100 feet. Okay, which is 1/100th. Okay, so and mathematically, the definition for the true error was essentially the relative true error was the true error over the true value. Okay, so you take the true error, which was defined as the approximate true value minus approximate value over the true value. Okay, so that makes that scales the true error that you measured, and you can add an absolute value on that as needed. Okay. Like I said, so typically we report these as percentages. We put on an absolute value, but if you want a signed error, whether you are over measuring, under measuring, you could totally do that. It's up to you as long as you are clear in your definition, like we discussed last time. And then we went over this example of the 1 meter error committed in measuring 100 meter bridge and a 10 meter suspension. Same error, so we know one of them is going to be 1% and the other one was going to be 10%. So the 1 meter error on the 10 meter suspension is significantly more grave than the 1 meter error on the 100 meter bridge. So you all know this by now. Okay, so that's a summary of the definition for true errors, and you got the true error and the relative true error. Okay, but I'm going to make a claim here now that true error does not make sense. And I want you to take a minute now to think about why true error does not make sense. You can flip through the slides and see the answer, but then I'm going to ask you why, and I'm going to dig in more details. So take a moment and think about why true error does not make sense. I'm going to start a 1-minute timer. I'm testing my green screen and the transparency, how well it's working. If you have an answer, please do volunteer, do speak up.
Is it because the true error requires the actual value, and in a lot of cases, we don't actually have the actual value. We have what we recorded, which could have an error in it.
That's correct. That's correct. And so if you had, so I'm sorry, I didn't see who was speaking. Who was that speaking?
Oh,
Mitchell?
that was me, Mitchell.
Yes. Hi, Mitchell. Nice to see you. Okay. Thank you. So your
Professor.
colleague is saying, yes.
Oh, I was just asking you to repeat it because for whatever reason, my internet decided to cut me out of the Zoom for a minute.
Oh, you would like me to repeat what?
Just what Mitchell had said.
Yes, so I'm gonna go ahead and cover that. So your colleague is saying that we don't have the true value. Really, in real life, we don't have the true value. If you had the true value, you wouldn't need it to do an approximation, correct? If you had the actual solution for a problem, you don't need to do any approximation. You got that and you can run with it, correct? So in that sense, the true error does not make sense because we really don't know it, okay? Now, except for certain cases like, you know, someone brings you a device and the spec says, or like you're doing air conditioning and the spec says that this should be 300 cubic feet per minute, and then you go measure 299, for example. Then you can define a true error in that sense. But in most cases, the true error doesn't make sense because if you had the true value, you don't need the approximate value at all. However, there are situations where when we are developing numerical techniques, And you will see that as we move along, like when we are doing Taylor series, oftentimes in my research, when we are developing new algorithms to solve the fluid flow equations, we need to test how well our methods are performing, okay? And to do that, we need some canonical cases, some like toy problems, if you wish, to test how well our methods are behaving against those toy problems. So in that sense, we define the toy problem. We know the true answer for the toy problem. That's like saying, I'm gonna try this method on a problem where I have the exact solution. Clearly, you have the exact solution. I'm not interested in solving that problem to get a solution. I'm interested in testing my algorithm and how well my method performs. And how do I hold my method accountable? I hold it accountable by saying, okay, this is the error committed when I'm solving such and such exact problem. So I described this here for you. So except for the case when validating numerical methods, where the presence of a true or exact solution can help assess the quality of a numerical technique. Okay. So now that we're done with the true value, what do we do with the true error? What do we do in real life? So like I said, in real life, we don't know the true value, or we're talking about complex problems, right? We don't know the true solution. So instead of looking for the true error, we introduce the concept of an approximate error. So just trying to give us a sense of the level of error we are committing. So let me give you an example, and this is an actual example that we encountered. So when we went down, I don't know if any of you attended my talk at Auburn last week, when we did the study for the Utah Symphony at Abravanel Hall. So we had to go down and take measurements ourselves for the air conditioning. And we had different devices. We had like these handheld fan anemometers, and then we had hot wire anemometers. And those different devices, they range from like the $20 piece, you know, to the $1,000 device. And you'd think that the cost is associated with the higher precision and accuracy. And so, and that was true. But then, you know, we did a measurement with the handheld anemometer, and the cheap ones, we had many of those. But, you know, we didn't know the true value for the air conditioning. But then we took the hot wire anemometer, where we knew we were going to get a better answer, but we only had one of those, and we had to return it in like an hour. But we needed to spend 7 days taking measurements. So what we did, we took a few measurements with the hot wire. That was the high precision calculation, if you want. And then we compared with the measurement taken by the fan anemometers, and we quantified the error, and we called that the approximate error. So in other words, we treated the higher accurate device as the true value, although it's still not a true value. It is still an approximate value, we know that. But we did a relative comparison with the higher accuracy device to the lower accuracy device, and we call that approximate error. That's actually the definition of approximate error. And so mathematically, we're going to do the same thing. We had true error, relative true error. We're going to define approximate error and relative approximate error. Okay. So approximate error is defined as the error between a current approximation and a previous approximation. That's definition 1 of the approximate error. What does this mean? What is a current approximation minus a previous approximation? Typically, in many numerical methods, okay, let me explain to you. In many numerical methods, there are things that are repetitive. So take a Taylor series, for example. You add one term, you add a second term, you add a third term, you add a fourth term. Every time you add a term, you're making a new approximation. So the approximate error, this definition of the approximate error tells you, take the most recent approximation that you calculated, and from that, take out the previous approximation, or take the approximation you took with the new device minus the previous device. Okay, so that defines just an approximate error. Now, there is an intrinsic assumption here that the new approximation, or the current approximation, is supposedly a better approximation than the previous one. In reality, that's the case with most converging numerical methods, because these numerical methods, they're repetitive in nature. You're just adding terms, and every term you add, you are getting a better approximation. So what you do, you take the new approximation minus the previous approximation, you take the difference, and you define that as an approximate error. Okay, so here's an example. Like I said, a vast majority of numerical methods consist of repeated calculations, such as when you evaluate functions on your calculator, like the sine, exponential, logarithm, etc. Actually, your calculator behind the scenes and your Python and other codes, they're doing Taylor series. And assuming that you were introduced to those in high school. So a Taylor series of a rational function, a real valued function, is simply a summation of terms. It's a polynomial, an nth order polynomial, and you just keep adding terms and terms and terms to the polynomial. For example, for the sine function, you got this sine x, equal this summation, x minus x cubed over 3 factorial plus x to the 5 over 5 factorial, and so on and so forth. And you just simply substitute the value for x over here. Same thing with the exponential. You got a summation for that. So those are the Taylor series. Now, clearly, you cannot add an infinite number of terms, right? But you can only add a finite number of terms. And this is where approximate error comes in handy, where you could say, okay, I'm gonna keep adding terms until the error is less than 10%, for example. What is that error? It's the approximate error. What if you add one more term? What is that gonna do to how is that gonna improve our approximation? Is that gonna improve it significantly or not? And that would be your error, okay? So here's an example. Now I want you to, we're gonna do this individually today, these activities, until I figure out a better mechanism for these breakout rooms. I'd like you to spend a few minutes and then go by hand, use the Taylor series, this Taylor series for the exponential function, okay? Use this Taylor series to add 1, 2, 3, and 4 terms, and report the approximate error. So that's the approximate error, current approximation minus previous approximation for each one of the four. When you're adding one term, 2 terms, what's the error between 2 and 1 term? What's the error between 3 and 2 terms? What's the error between 4 and 3 terms? Okay, so calculate that approximate error. Do this by hand. Think of it as a table. You got terms. So, and by terms, I mean, so a one-term approximation is simply the first term in the Taylor series, would be 1. Sorry, 1. A 2-term approximation would be 1 plus x. A 3-term approximation would be 1 plus x plus 1 over 2x squared, okay? So go ahead and spend 3 minutes on doing that. Get your way. Do an effort to do it yourselves. Don't look through the slides. It's not going to help you. Okay, just try, make mistakes, right? Make mistakes. That's the purpose here. You make a mistake and then you figure out what your mistake was. Okay. So again, the approximate error is the current approximation minus the previous approximation. How are we doing? Good. Okay, almost out of time. Again, I encourage you to turn on your cameras. You don't have to, but you will have to turn them on during the all exams and quizzes, okay? All right, I'm gonna call time. All right, let's see, do we have an answer?
Well, I mean, as expected, as we added more terms, the approximation between term 3 and 4 was 1.3 versus terms 1 and 2 and 3 and 4 were just 2. Or sorry, yeah, between the first two terms.
Okay, so let's see what I got. So for what I have here is the solution for x equal 2. So we're evaluating the exponential at x equal 2. And I'm gonna start calculating errors for each term. Clearly, when we have a one-term approximation, the error is undefined, right? Because you don't have a previous approximation. You probably could say the initial error is 100%. Okay, there's no previous approximation. Now, when you have two terms, you're adding 1 plus x, that's 1 plus 2 equals 3. And then between the error, which was the current approximation 3 minus the previous approximation 1, so that's 3 minus 1 equal 2, just like Sarah said. With three terms, again, we're adding 1 plus x squared over 2. Now, notice what I'm doing here in the slides. I'm taking the previous results, which is 3, and then I'm adding it to the 1 over 2 x squared, okay? So then you get 5 minus 3, current approximation minus previous approximation is 2, again, and then all the way you go to the 4 terms, and then you get 1.3 as an approximate error, okay? Does anyone want to object to this way of calculation? Okay, again, I cannot see you, unfortunately, because your window is like behind this window that I'm looking at. So please do speak up if you have any objections or concerns. Okay, so let's move on. Now, the approximate error is also defined as a more accurate approximation and a less accurate one. That's kind of the definition I led with when I told you between the different measurements, the hot wire and the handheld, the fan anemometers, right? And actually, this is exactly what happened with the Taylor series. We know with the Taylor series, it's a convergent series, which means the more terms you add, the closer you are going to get to the solution. You're not going to get farther away. So more terms mean better, more accurate approximation than the previous terms. And so another definition of the approximate error is a more accurate approximation minus a less accurate approximation. Okay, and we're not going to do this activity, but I'll do this example with you. Here's an example of how you could define a more accurate approximation, but not in the context of adding terms. This is just taking two different ways of calculating something, knowing that one of them is more accurate than the other one, and defining an error based on that. So again, we go to the example of the first derivative, which we talked about last time. The first derivative of the function, any function, any continuous function, can be defined as f prime of x equal f of x plus some number h minus f of x over h. Now, h is a small value, and clearly we know that if as h gets smaller, this approximation is going to get more and more accurate. So this question is saying for the function 2e to the half x, which we did last time, find the approximate error in evaluating f prime of 3. So we're evaluating the derivative at 3. Again, these problems are kind of made up. There's not significant practical significance, except to train you in these concepts now, okay? We're using h, so we're going to calculate the approximate error in evaluating f prime of 3 using two values of h, 0.5 and 0.05. So we know that with 0.05, we're going to get a better approximation, because by definition, the derivative is, this definition of the derivative is going to be more accurate with the smaller the value of h. So this gives us a way to define an error between h.5 and h.05. So you just go ahead and do that. I'm just going to spit out the solution for you. I urge you to do this at home to verify this for yourselves numerically. So with h equal 0.5, what you get is an approximation of 5.09, whatever that value is. And for the smaller value of h, which suppose is going to give us a better approximation, you get f prime of 4.5, the more accurate approximation. And then you define the approximate error as the difference between absolute value difference between these two values, or a signed value, however you want to define your error. Okay. Okay. Now this again does not tell us how large the error is. So, you know, we commit an approximate error of 0.5. Let's say you just by chance you happen to commit the same approximate error, and you're like, which one is bigger? Which one is more grave than the other one? So this leads us to define a relative approximate error. So same thing what we did with the true error, relative true error, approximate error. Now we're going to define the relative approximate error. And guess what we're going to do? We're going to take the approximate error, okay, and simply divide it with the current approximation or the higher accuracy approximation. Now remember, when you compare to the true error, we said in the context of approximate errors, the current approximation or the higher precision or the more accurate approximation is treated as if it's the true error. Okay, so we hold everything accountable to the more accurate calculation. Okay, so that's why we divide by the current approximation, not the previous approximation. Okay, although it won't be a big deal, but it's good. It's good practice to do this. Okay, and typically we report these errors as a percentage and in absolute value, unless you want a signed error, signed relative approximate error, whether you're above or below kind of a standard value, but you multiply by 100% to report things in percentage. Okay. So now again, I'm going to ask you to repeat the Taylor series example, which you already did. Now take the values that you got. Okay, same exact problem. Now take each value that you had only calculated the approximate error. To do the relative approximate, you simply have to divide, take that value that you calculated and simply divide by what? By the current approximation. Okay, take a couple of minutes to do this, please. You can look at the slides, at the previous slide with my answers, and just simply calculate the relative approximate error. So again, you're taking the approximate error and dividing it by the more accurate or the current approximation, okay, which has the more terms.
Professor, just to double check, the approximate error, any approximate error, you need a current trial and a previous trial in order to use either the relative approximate or the
correct. Either a current trial or a I wouldn't call it trial. You know, yeah, you can call it a trial, but think of it as a more accurate calculation. Okay. Okay. Call it a more accurate calculation. Now, in the context you're speaking of, where you're doing an experiment over and over again, you can still define an error there. And once you reach a point where there's no difference between your trials, or the difference between the trials is minimal, you've reached the best you could do with the system. Okay, so that's like an extra thought to think about. But yes, you are correct. You need these. You need two values. Okay. Let's see how everyone is doing. So typically, when doing these activities in the classroom, the class would be buzzing and people talking and being loud, etc. There's a lot of silence here. But I understand, imagine turning all the mics at the same time, it would be quite overwhelming. All right, so time. Who's got an answer for me?
I can show what I got. So
Yeah.
between the
ahead.
first and second, the relative approximate error is 2/3 or 0.667.
Uh-huh.
Between the second and third, it's 0.4. And
Uh-huh.
between the third and fourth, it's 0.21.
Correct. Yep, that's exactly what I got. So thank you, Sammy, for volunteering. So let me share my answers with you. So again, the first term, we don't see. So with the first term, you don't have an error because you don't even have a previous value. Or you could think of it as an error of 100%. You know, this is like full error. Now, with two terms, we defined that's the numerator, that's the approximate error. Sorry, that's with two terms. That's the answer with the two terms. And then the error is the approximate error on the numerator over the current approximation, which is 3, and that gives you a 66.7%. Now you see how we have a better sense of this error as we go down, and we expect it to keep shrinking and shrinking as we add more terms. So that's the power of the relative approximate error. Okay, I really like relative errors. It gives you a sense of how large things are. Okay, do you have any objections? Any dissenting comments? Okay,
It's not a dissenting comment.
go ahead.
What does the relative error? Relative error just means the difference between your current approximation and the previous approximation. But how well does that relate to the true error? Like, I know it's a completely different idea, but does it relate to it at all? Or is it entirely just error from one approximation to the next?
So let's do some let's philosophize a little bit. I don't know if that's even a word. Let's think about this in a moment. In the absence of any access to true values in reality, you have a system, let's say, that's computing things. You have a computer or a calculator that's computing things. The approximate error or the relative approximate error, what they tell you is the best you could get with the device you have. You might be far from reality, okay? But the best you could get with the device that you have, with the method that you're using, can be measured by the approximate error. So take the example of trials that your colleague did earlier. Let's say you have an experiment and you're measuring the flow rate of some quantity in your separations unit, okay? And you measure and measure and measure, and then take the difference, and then you reach a point where like all your errors are less than 1%. Now this might be far away from reality, but with the device you have, that's the best you could do. You've exhausted all possible ways to improve your calculation. So that's what approximate error really does for you. Okay.
Okay, I see now. Approximate error is a method by which to tell how well your method is working. Exactly.
And you will see as we move on with our calculations, once we get to linear solvers and iterative solvers, you might be far from you might not be on spot with reality, but the best a method could do, if you get to like 0.1%, that's the best your method could do. It cannot do any better. Okay, so in a way, that's what it measures. Now, you should be reassured that, again, when I say a method converges, all well-designed numerical methods, they converge to the true solution. So we know that we are close to the true solution. We might never know the distance to the true solution, but we know the best we could do with the device we have. It's going to depend on your calculator, on how many digits you carry, on your computer, all of those things. Okay, we'll get to see more of this as we move on.
Hey, Dr. Saad, I have a question.
Thank you.
Real quick.
Brandon.
With the current approximation, I feel like
can you repeat?
Yeah, can you hear me now?
Yeah.
With the current approximation, I feel like you said it's an improved approximation. Doesn't it imply some kind of knowledge in relation to the true value, though? If you don't know the true value, how do you know you're improving? Do you just assume each improvement?
No, I know I'm improving because the method is convergent. So I know that all Taylor series, they converge to the true solution. By converge, I mean every term I add, I'm getting closer to the answer. Okay, so therefore, an approximation with 10 terms the current approximation is better than an approximation with 9 terms because I know the method is convergent. Okay, so that's how I can tell that the current approximation is better. Now take the derivative example. We know that with a smaller value of h, we have a better, by definition, and you can prove this, we have a better approximation, okay? Was this
Thank
clear,
you.
Brandon? Okay. All right, great. Notice yes.
If I can ask quick, so for careers, homework, and beyond, are we going to want to be expressing errors as percentages? Just to clarify.
It's up to you. It's up to you. I like percent. Typically, people use percentages. Yes, you know it because it gives a sense of you know, out of 100%, that's the error, right? But you have to judge depending on your audience. You know, you have to tell kind of what error you want to report. Like I said last time, when we're developing numerical methods for fluid flows, we look at all the errors, every possible definition of errors in different quantities, and just we try to weave together a story, and then you weave the story to tell the best, the punchline essentially. Percentages are the most relatable to people, right? So ask yourself, when we presented the errors as 66%, 40% versus 0.3 or 2, you know, 2 didn't, what is an error of 2? It doesn't, I don't know what an error of 2 is, right? But an error of 40%, that's a big deal, right? So yes, percentages. Okay. All right, let's start moving on. So how can we use this in practice now? And we're gonna get our hands dirty with some programming now. Before you read the problem statement, I want you to go on your Canvas and into the files directory, and there is a Jupyter Notebooks directory, and under that there's a folder called errors. Open it, and there is a relative approximate error with gaps notebook. Download that and upload it to your Jupyter Hub, or if you're using locally, put it in the appropriate directory, okay? While you do that, I'm gonna switch screens and we're gonna try to work on this together, okay? This is gonna be a coding activity, and to explain to you what we're gonna do, we're gonna write a Python code. So we said, okay, how do we use this relative approximate error in practice? We're gonna write a Python code that uses the Taylor series to calculate the exponential function down to a certain tolerance, down to an error. So you come and ask someone, hey, I want you to calculate the exponential of 5 down to an error of 1%. Okay, so this is where we're gonna use relative approximate error, okay? While you download the notebook and upload it, I'm gonna switch screens, okay? I'm gonna switch screens. Okay. On my end, I have Jupyter Notebook right in front of me locally, and so downloaded, installed locally, so I don't have to go on Jupyter Hub. Now remember, on Canvas, you get the file, you upload it on your Jupyter Hub, or you put it in the directory where your local installation is. And let me see. Did anyone not find the Jupyter Notebook in question? It should have with gaps in it. So this is a technique I introduced last year where I put some code for you and I leave question marks here and there to give you a kind of push initially in what kind of programming we're doing, but you're gonna have to fill in the gaps, okay?
I'm sorry, Professor, I couldn't find it. Could you tell us where it was one more time?
So it's under files, Jupyter Notebooks, errors. It's the one on relative errors with gaps, okay? Is anyone else not seeing that? Let's see, it's called Taylor series relative error hyphen with gaps. So I'm gonna share my screen now. And I'm gonna, so you should be seeing something like this. Okay, so I'm sharing my screen with you now. Is this what you're seeing? Perfect. Okay, so I got some, okay, we're seeing this, okay. All right, are we all on board? Okay, I'm gonna assume yes. If you're not on board, speak up, I cannot see the chat. There were like 1,000 windows in front of me. Okay, so write a Python code that uses Taylor series to evaluate the exponential function down to an error, also called tolerance, of 1%. Now recall that, okay, I have a repetition here. Recall that the exponential function is defined as 1 plus x plus 1 over 2 factorial x squared and so on for all x. The idea here is we want to keep adding terms until the desired tolerance is achieved. Now, in this notebook, you're going to see a bunch of things here first, where I kind of pre-programmed some items for you for simplicity. So I'm importing the math module. So if you had done your homework, you would have gone through this already. The math module is going to define the exponential function and the factorial function for us. We need the factorial to calculate the Taylor series, but we also need the exponential to try to compare to the true error to the true value just out of curiosity. Although we're only calculating relative approximate errors over here. Okay, now the first couple of cells, I'm not gonna go over them. They essentially, if you're new to programming, you would probably do this by hand. Essentially, you do term 1, term 2, term 3, just like we did by hand on the slides. While this is a way to do it, it's a terrible use of programming. You're just using Python as a little calculator, which essentially you don't need. You don't. Using a more powerful tool than the task needs. So you don't want to use Python that way. However, what we want to do, we want to use Python to do repetitive tasks. So you will notice that you're adding 1 term, 2 terms, 3 terms, 4 terms. It's a repetitive task. So it's like there's a counter and you're adding things. So happens that there's a for loop in software, in programs, and we're going to use a for loop to do this. First, I want you to go ahead and play around with these for loops. So let's do a for loop. In a for loop, you can do repetitive calculations for a specified number of times. We typically use the Python range function to create a counter that we can loop over and repeat. So all you want to do is like add 100 terms. You need a counter. Term 1, term 2, term 3, counter 1, 2, 3, 4, 5, 6, 7, all the way until you reach 100. And you create that counter with the range function. The range function takes 2 arguments, a start argument and a stop argument. And it will always go from start to stop -1. So if you do from 0 to 10, it's going to go from 0 to 9. If you do from 1 to 10, it will go from 1 to 9. If you go from 5 to 10, from 5 to 11, it will go from 5 to 10. Okay, so play around with this. I printed this out for you. If you select the cell, press Shift Enter, and you'll get this. So what I'm doing here for I'm automatically declaring a variable called I. It's our counter. In range, that's the range function, start at 0, stop at 10, print the value of I. So that's my counter. So if we go from 0 to 11, the counter is going to go from 0 to 10, really. So you go from start to stop -1. Okay. Now check this out. You can go from -5 to 10. It's going to go -5, -4, -3, all the way to 9. It's just a counter. Okay, just a counter. Now inside the for loop, you see those the column over here, and then everything inside the loop is going to be you're going to add a tab to it. It means it's within the context of the for loop. Okay. All right. Now try the following. Here I omitted the start in the range. What happens in that case, it always assumes if you omit the start, if you put one value in the range function, it's always going to start from 0. It's just a simpler way. So if I put for I in range 10, it's going to go from 0 to 9. I in range 50, it's going to go from 0 to 49. It's still 50 terms. 0 to 49 is 50 terms, right? So that's what it will default to. Okay, 0 to 5. So we're going to use this to build our Taylor series. All right, so we're going to do this in chunks now and follow through with me as I go through these cells one at a time. Now we want to create a for loop that calculates the Taylor series of the exponential function. Let's think about this. What do we need to do this? We first need to define the value at which we want to calculate this Taylor series, right? So that's x, 1 plus x squared over 2, that x. We need to just declare it. We need to set a value for it. In this case, it's 2, okay? Next, we need a variable to store the result of the calculation, correct? So as we add terms, we're going to go over term 1 and then term 2, but we need to add it to term 1. Term 3, we need to add it to term to the result of 1 and 2. And term 4, we're going to need to add it to the result of 1, 2, and 3, right? So we're going to store that result as a sum, and we're going to keep incrementing it with the new terms, okay? We need to define the number of terms we want in the calculation. Do you need 10 terms or 1,000 terms? Okay, we're going to call this n terms, okay? And finally, we need the factorial function. We're going to use math.factorial of n. Sorry, math.factorial n. There's a typo over here. Okay. Now, in what follows, I created a base code for you, and you're going to have to fill in the gaps. Okay, so take a minute and fill in the gaps, please. I already defined x equal 2 for you. Now I want you to fill in the gaps. The next line is the result. That's where we're going to store our answer. Now you need to initialize your result with something. Okay, you need to initialize it with something. What is that something? Pick an initial value. Okay. So go ahead, take a minute. All right, time. Let's see. All right, I want you to start helping me now. And again, the more you contribute to these class discussions, I take those contributions into consideration in grading and things like that. So just so that you're aware, there's no like formal statement for that, but if I know who you are, if I know you're contributing and you're like on the verge, that will help your case. Anyway, just to encourage you, because I know many of you don't like to be called upon, and we'll have to figure that out as we move forward. But I'd like volunteers right now. So let's see, we start with x equal 2. That's where we define the x value. Now, what do we put in the result?
I put 0.
Okay, why?
Just because at that point, there's nothing, we don't have anything to go off yet.
All right, any objections?
Would something
Okay.
like 1 work also? Like if you just put 1 as your result?
Okay, so let's think about it. Abby is saying we are going to initialize the result with 1. Now let's think. If you start with 1, now this result is going to hold our summation, our calculation of the Taylor series. We're going to take result and we're going to start adding terms to it. What would happen if you had started with 1?
Oh, then you would be adding an extra term, like
an extra term, correct. You'd be adding 1, okay? If this were a multiplicative problem, I would start result with 1, because 1 multiplied by something is always that something. But because this is an additive problem, I want to start my result exactly 0, because I'm going to add these terms now. This is just to think of result as a bucket, okay? The bucket is empty. Term 1, term 2, term 3, term 4, that's how we're going to build this, okay? All right, so now, yeah, great, thank you. So n terms is 10. You can put 50, let's put 50, 30, whatever you like, okay? Now, for n in range, what is range?
Just n terms.
Okay, why?
We could either do 0, n terms, or that's the range, like from up a little bit.
Yeah, so if you think about the summation symbol, this is going from n equals 0 to n terms minus 1, or a total of n terms. Okay, a total of n terms. We want to add 100 terms or 5 terms. Go back to the counter. Okay, term 0, 1, 2, 3, 4, 5, etc. Okay, now what do we put in the result? So this is where we're gonna start adding all the individual terms. Okay, what are we gonna put in result?
I put result equals result plus 1 over n times x raised to the n plus, or the n minus 1.
1 over n.
1 over n. Yeah. And then that times x raised to the n minus 1.
To the n minus 1.
Yeah, because I started it at I started the n terms at 1, so that for the first term you wouldn't have 1 divided by 0.
Okay, so let's eliminate that and just keep it at n. Okay, so okay, can you justify that for me? Can you explain why do you have result equal result plus something? Okay, why do you have result here on the right hand side?
Because in the past that's kind of like the skeleton I've used for summation functions.
Yeah,
so that it would keep adding to itself.
Okay, so we don't know about what you've used in the past. I want an explanation of why this works. So
okay,
yes,
yeah. So for each time you add the previous value, similar to like we were doing in that exercise, we were practicing doing our approximate error.
Yeah.
It'll keep adding to the previous value, and that is what creates the summation.
Okay, that's great. So let me explain it in my terms. What we want to do. So what we want to do is start with 1 term. So we have our bucket called result. Okay, you want to add the first term on it, and that's like 1 over factorial 1 times x to the 0. That's 1. Then you want to take that and add to it term 2 and store that in the result. Okay, that's the bucket. Now you want to add 1 more term to result. You can just throw it in the bucket. Now the writing result equal result plus something, don't interpret this mathematically. This is not a equal a plus 1. No, what this is saying is the new value of result on the left hand side, that's the new value of result, is equal to the old value of result plus something. So think of it, the computer is going to treat this as memory. It's going to say, oh, I am going to assign result is a location in memory, is a bucket in memory. In that bucket, it exists, it's called result, it already exists, but in that bucket, I'm gonna take whatever already exists plus 1 more term. Make sense? So don't interpret this mathematically as a equal a plus something. That's not the case.
I've got a question if that's okay. So is this iteratively adding the Taylor series from 0
it is
to
iteratively
50
adding
or 1 to 50?
Pardon me?
Does this go from 0 to 50 or 1 to 50?
What do you think? What do you think? The way I have it written.
0.
Yeah. And if you're in doubt, print it out. Okay. So let's You are absolutely right. And I do this all the time. Okay. Print n. Okay. And you're going to see with that it actually starts from n equals 0. Now there was a little typo here. We need math.factorial of n times x to the power n. Okay. Now, after all of this done, we're printing the result. That's the final answer. And out of curiosity, I want to compare this with the exact value. Okay. So I'm going to run this. See, it did start from 0 and it went to 49. That's 50 terms. Okay. The value we calculated is this. The value that was given to us from math.exponential is this guy. It's pretty close. Okay. So let's do this with like 10 terms, for example. Okay. Okay, now you can print also the result at each calculation, okay, at each step. So print print n, so with n terms, the result is, with 0 terms, the result is 1. With 1 term, the result is 3. With 2 terms, the result is 5, and so on and so forth. Okay. Now, this is great to verify your programming and your coding, because I had advised you when you're looking at something, do a calculation by hand for a few terms, okay? Just to figure out what you're up against. All right. So now we're going to take our calculation. That's great. Now we can calculate the Taylor series for a given number of terms. Now I want to calculate the error. Okay, which error is going to be the relative approximate error. Okay, I want to calculate the relative approximate error every time we add a new term. Okay, so how do we do this? I have a pseudocode here for you. We will need to make a copy of the previous approximation. Let's call it old result, and compare it with the new result. So once we enter the for loop, we need to grab the old value of result and make a copy of it. Okay, hold it. So hold. Okay, so let's say you already calculate 3 terms. Now you're calculating 4 terms, but all we have is one variable called result. What we need is we need to take the result with 3 terms, put it on the side. Okay, I don't know what they used to call this with like actually physical calculators, but put it on the side, calculate a new value with 4 terms, and then take the difference. Okay, so I have a pseudocode here for you with question marks. I want you to spend a minute on trying to filling in the gaps here. Okay. Remember, excuse me, a result contains up to however many terms you hit in the for loop. Okay, so when you enter the for loop, you already have a value for result. We're going to use all the result to make a copy or to hold that value on the side temporarily. Okay. All right, time. Okay, so let's start. Everything is the same as we explained before here. What about all result? What are we gonna do here? I want new volunteers.
We would just put it as a result.
Okay, why? Why?
So when it runs through the program, it's taking the previous result before it updates it.
Exactly.
So you're
exactly.
taking yeah.
Thanks, Rob. So what Rob is saying is, in old result, we just take whatever is in result, whatever is in our bucket, we make a copy of it, hold it on the side. Then we're gonna update result, and then we'll calculate the error. Okay. So who's gonna help me with the error?
Would it just be also result because now the result's updated?
No, but what's the error?
Not just
We
the
want-
equation.
Okay, so what is that?
The absolute
Result
value.
minus old result
Okay,
divided
absolute
by
of
result.
result, minus old result. And if you press tab, here's a little trick, tab, it will auto-complete the variable for you. Okay, over result. So old approximation over, you can put them all in under absolute value, okay? Result minus old result over result times 100. That's gonna give us a percentage. Any objections? Yeah. Okay, let's run this. I love it when it runs. Okay, so error for term 0 is 100% by definition, because we started, with, we don't have any knowledge. Error for term 1 with one term, error with, let me put it this way, n terms. Okay, error with one term, two terms, 40%, three terms, etc., and so on. And so you see how we can start converging. Okay, so now we are still missing one piece. I can put 100 over here. Let's put 100 terms. Okay, but 100, we're like reaching 0% pretty quickly, right? We reach 10 to the minus 14, but so there's no point in doing anything. We'll learn later that this is beyond machine precision, what the computer can actually calculate. We just spent time calculating from term 20, from 23 terms to 99 terms with no improvement whatsoever in the error. So how do you tell this to stop? That was the original question, is I want this to stop after we reach a certain error tolerance. When our error is less than 1%, that was the question, I want the code to stop. Okay, so this is what we're gonna do next. Okay, so now we need the for loop to stop after a certain tolerance. I'm repeating myself. We need an if statement now to track the error. Okay, and once the error is below our tolerance, we're gonna stop. All right, plain English. All right, so this is the code for this. You only have two points with question marks. I added question mark on n terms, and I also added question mark for the if statement. All right, you got a minute? Even if you can't write the if statement correctly, the syntax correctly now, just write it in English. Okay, just say if this is less or greater or whatever than that. Okay. Three seconds. Okay, time. All right, new volunteers.
So you just tell it when E is equal to 0. So E and then 2 equal signs 0.
So, okay, so let me, help me spell this out. If E.
Then space, and then equal sign. And then 0.
0.
Well, E won't ever equal 0. Don't we just want it when E is less than tolerance?
Is that Nathan? Nathan?
Carson.
Carson, sorry, I can't see I need to pin the, I can't. Okay, Carson. Yes, you are correct. So Carl suggested if E equals 0, we're gonna stop. Do we ever reach E equals 0? And would you want to stop at E equals 0? No. So, and that's not the question. In this problem, we're gonna reach 0 just because it so happened this way. But in actual problems, you're never going to hit a tolerance in a relative error of 0. So what's going to happen to you is just going to keep looping and looping and looping and looping. You're going to just lock up the computer. But our question was, if the error is less than the tolerance, just like Carson said. Okay, so Carson, do you want to spell it out for me?
Yeah, so I just set my end terms to something high because it doesn't matter since it's going to break.
Yeah.
It's going to break
Okay.
anyways.
Okay, so that's another point. Let's just do this right now and we'll explain it. But if E is
less than tol, T-O-L, and then
good.
that should
Okay.
that should work.
Okay, let's run it, and it does work. And it says it took us 7 terms to get to this tolerance. All right, so let's see what Carson suggested. We had defined our tolerance as, let's define it as 1%, okay? And we're gonna tell the for loop to keep looping, adding terms until we hit the 1%. But your end terms needs to be high enough to give it a chance to hit 1%. If we had put 2 terms in end terms, we're not going to hit 2%. We hit 66% because we didn't add enough terms to reach 1%. What if we do 4 terms? Again, our final error is 21%. We never reach the tolerance. So Carson said, let's put like 100,000 terms here because we know it's going to break before that. Okay. And indeed, we gave it enough room to add terms until it hit this tolerance. Okay, any objections? Any dissenting comments?
I have a question.
Yes, Sammy.
Maybe a bad idea while we're still learning Decoder, at least for me, to put like 100,000 in case for some reason it doesn't break and it like freezes up.
Can you repeat? Did you put 100,000? Sorry.
No, I only did 100, but I was just saying.
Oh yeah, absolutely.
Just
yes,
smaller number.
I gotcha. Yes, that's what I would do when I'm experimenting with code, and I'm like, oh, I don't know if this is gonna work or not. I put like 2 terms, and just to get an idea of what's happening with my code. And you're spot on, Sammy. Good. That's a very good practice. Good advice. That's the tip of the day from Sammy today. Really, is like don't put like 1 billion terms. Just like start with a couple of terms. Make sure it's calculating things correctly. Thank you. Okay. Now in the last cell, I have another way of solving this problem using a while loop. I leave that up to you to try to comprehend. We'll go over a while loop example later. But right now I'm gonna stop here. Let me see where we're at with the slides and the time. Okay, so we got about 10 minutes. Now I want you to head on to, I'm gonna stop share. And you're seeing me with my green screen behind me, right? Okay, so now we are gonna go to Canvas and you're gonna have a quiz. Okay, so I'm gonna go and unlock the quiz for you. It's just like a 5-minute quiz. Okay, that covers material from last week. Can I go ahead and unlock it?
Will the quiz be found under quizzes or assignments?
Under quizzes, but I have not released it yet. So give me a moment. And once you start taking it, okay, let me see, edit. Okay, so you're gonna have 5 minutes for your quiz and you should be able to see it. Go ahead and get started. Please turn on your cameras.
What should I do if I'm on a computer that does not have a camera?
It's okay.
Okay.
But do plan for Thursday's exam to have a camera, please, because that's gonna have work by hand. And it's not like I'm gonna detect you cheating, but if like someone blatantly comes behind with like a board and showing you the answers, I'm gonna tell you, you know, don't look at that.
Okay, yeah, I can use my phone for my camera then for the test.
Okay.
Can we go forward and backwards between questions, or is it once we submit question 1, it's done with, and now we're on question 2?
You can, I think you can go back and forth. That's I enabled that setting, so. But you'll see one question at a time, okay?
Should we have our notes put away?
I don't care.
Professor Saad,
Yes.
so there is, the question 4 asks, and larger true error always means that a worse error. I don't really understand that question. Would you be able to explain it?
Which one of that was that?
Question 4.
A larger true error always mean that that's a worse, sorry, it was, I must have, okay. A larger true error always mean that the error is worse. Okay.
Thank you.
Okay, sorry. So a larger true error always means the error is worse. I updated the phrasing for some reason. It was typed incorrectly, I apologize. I wouldn't look at your notes, you know, try to retain this from your deep mind, okay?
Professor?
Look at your notes, it's not gonna help you, yes?
The question 4, a larger true error always means that a worse error.
I just explained that, Natalie. I did edit it. It probably didn't show up on you. It essentially, the question is, does a larger true error mean that the error is worse? So I edited that. It probably didn't show up on your end. I apologize for the phrasing. There's a typo there, but again, one of the questions asks does a larger true error always mean that the error is worse?
Okay, thanks.
Okay, you should be almost done, most of you. You'll see the answers at 12:05. Okay. I'm looking at the scores as we see. Okay, there's about okay, so there's a few who started late. I'm just going to go ahead and continue the discussion briefly. So for Thursday, you're going to have your exam 0. It's going to be a short exam, about 10 to 15 minutes, and it will cover your prerequisites, similar to the sample exam and the study guide that I put there. Make sure you leverage the help sessions if you have any kind of gaps in your prerequisites. And before I let you go, I'd like some feedback on two things. So first, how do you like the new style of the lectures?
It's awesome.
This is great. It's so
Excellent.
much better. It's very interactive.
Yeah. Do you think this is going to keep you more engaged as we move on with the semester? Okay.
Absolutely.
Okay, thank you. And so, but the risk is, I'm going to try to get one more monitor to put the Zoom window over there, but I'm going to have a hard time seeing questions or chat messages. So I encourage you to speak up, please. Or, if you see a chat message, someone didn't want to speak up. I think I think you should be comfortable enough with me and the class to just speak up. We're not going to criticize any comments you make, or any of that. Just feel free to communicate, because I don't want to miss a question that you have. Okay, but if someone asks a question on the chat and one of the colleagues feels like, oh, there's a question that wasn't addressed and I missed it, please speak up on behalf of your colleague and say there's a question, just to help me. Typically, I would have the TAs monitor that, but they have classes during this time. Okay, so we'll continue working with the green screen. I was ironing it this morning to remove the wrinkles, but yeah, we'll make this an asset. Okay. All right, so I wish you luck for Thursday. We will start the class with the exam. Again, get your note sheet. Please do get a camera. Do not cheat. Rely on yourself. No, you don't win if you're cheating and just to get an answer. Okay, and all right, best wishes. Let me look through the chat messages before. Yep, the setup is great. Yeah, great. Thank you. Okay.
Professor, I had two quick questions.
Yeah, go ahead.
Before you leave, if you mind. Number one, for that fourth question, a larger true error always means that it's a worse error. Why is that false?
Okay, so let me make sure everyone finished the
oh, my apologies.
the exam. So let me give you this example: a 2-meter true error in measuring a 100-meter bridge versus a 1-meter error in measuring a 10-meter table. So that's an example where a true error is larger. It's 2 meters, right?
Oh,
1 meter. Yeah, that's why we take the relative error.
I was thinking of it as a worse error, meaning that it's farther off.
So if you're measuring the same, yeah.
That would be the relative true error, not the true.
If you're measuring the same thing, if you're measuring the same thing, then yes. But in general, that's not the case. Okay, we're kind of comparing different measurements and so on. So, but good question, Braden.
I see my misunderstanding in my thought process. The second question that I have was regarding the homework. So in problem 1, it says go through the Easy Pi slides, which I've pulled up, and attempt to replicate those in your own Python notebook. And then it says you don't need to submit anything for this question, but it's worth 50 points. So how does that work?
Good luck, free 50 points. But trust me, it's gonna catch up with you if you don't do it. You're gonna get behind. You're gonna miss things, and if you come with a question like, how do I define a variable? I gotta tell you, you know what? You go and do the slides. We covered that. So
okay, that's what I was just sitting here confused about, because it says attempt to replicate it, and then it says you don't need to do anything.
You don't need to do anything, because I cannot really, you cannot prove to me that you went through the slides, and you can go through them blindly, but it's it's up to you to kind of dig in and understand. Okay. I was feeling generous when I wrote that homework problem.
Okay. And like I said, that was just me reading through it and saying, what in the world? Like, I don't know if he had a typo there, if he meant to say that, what he means by it, but.
No, there's a sense, and I want a sense of personal responsibility as well, right? That's something I learned when I came to the US, and I would like to reflect that with my students. You know, you're adults, and I want to trust you, and I want you to trust me that you're gonna do the right thing, you know, for you. Okay.
Okay.
All right. Any other comments? Yeah.
I guess my next question would be, in this class, it obviously has it has a reputation, that's the word I'm looking for, of being a very interesting and difficult class. What tips and tricks would you give to somebody who hasn't taken this class before? Like, what material would you say really study and focus on? Because this is the material that people struggle with the most.
I typically find that, so the class is split in a distribution, and that distribution, and there are two aspects of the class. There's the theory, the thinking of what's going on in numerical methods. If you think about this class, it's just essentially a set of tools. We're not even touching on the deep theory. We're just learning tips, tools to solve this type of problem, that type of problem. So for example, calculate an error, solve a linear system of equations, do a data fit, do a numerical integration, numerical differentiation. So it's just tools. Think of it as tools to solve all of these problems. We don't get into the theory of how we're, like theorems and the math behind the tools. We just get enough into how we develop those tools, just enough theory into how we develop those tools. So you got to understand the theory properly, and that is critical thinking. That's where critical thinking comes in. So, you know, when you're thinking about errors, next we're going to talk about linear systems of equations and how to represent them as a matrix, and, you know, thinking about that. But then there's the programming aspect. So if you cover the theory, that will get you quite far in the class, because all exam problems are based on the theory, essentially on the understanding of the methods. Okay, so questions on the exam wouldn't be, I will not ask you write a code for the Taylor series of the exponential. I will ask you, you know, while calculating the exponential, which type of error would you use to stop at a tolerance of 1%? You're going to be able to say, you know what, that is going to be an approximate error, and it's probably best to do the relative approximate error. Okay, so that type of understanding. So that will get you quite a ways, you know. And if you, I've seen some students who didn't do the programming at all, but they did so well with the theory, and they were able to just barely pass, you know, because they covered the exams and the quizzes, and that gets you just enough of a grade to pass if you're just thinking about passing. But then comes the programming part, and that's where, you know, if you're struggling with the theory and you're struggling with the programming, typically it's hard to find someone who doesn't understand the theory but understands the programming. They go hand in hand. Okay, so if you don't understand the theory and you don't understand the programming, then you're in trouble. Okay, if you understand the theory, then you got to work on your programming, because that's where we take those tools and implement them at large scale. And that's what homework is about. It's mostly about taking those tools and putting them to use with code. But that's why homework is, because again, this class is not about programming. It's about using programming to solve problems. That's why homework is about 20-25%. Okay.
Okay.
So, but so in terms of material, I would focus on programming, because conceptually, and I try to explain as best I can with my slides and the lectures. You can learn with me well in class. If you follow me, if you follow the lectures, I think, you know, and based on previous feedback, that, you know, I try to deconstruct very complex concepts into small bits and pieces, and then to get an understanding. But you got to follow that. But in terms of prep, I would focus on the programming, okay, on getting better at programming, thinking, about programming, copying others with programming. Just that's how I learned programming. I would copy what's out there and adapt it to what I'm doing, and then there's always an aha moment. Excuse me, and that will essentially, then you'll be in really good shape.
And then one more question for the quizzes and tests. Are we allowed to use any notes that we've taken in the class? Is it open notes and open homework, or?
So I explained for the exams clearly in the syllabus. So go over the syllabus in more detail. And for each exam, I put a reminder on the front page. So if you look at the front page for Canvas, I explain clearly what is expected on exams. For quizzes, don't use notes. Because these are going to be pop quizzes. You don't even have a chance to open up the slides and find where the question is. So I don't expect you to look at your notes, but I cannot see what's on your screen. For the exams, depending on what exam you're taking, exam 0, 1, 2, or 3, look at the syllabus has the details, but you're allowed to have your own sheet, double-sided, etc. And so hopefully that's clear in the syllabus. So for exam 0 on Thursday, you can have a letter size double-sided sheet. All right, so I'll let you take up any more questions in the office hours today from 3:30 to 4:30. Okay, I'll be on Zoom, just hop in. Okay. Thank you, everyone.
Thank you.
Thank you. Bye-bye.